steps in non-topological regime.
Hi everyone, thanks for the kind introduction. So today I'm going to present work that has been carried out in Professor Javad Shabani group. So that's an experimental work, and we receive theoretical support from the group of Enrico Rossi at William and Mary. So today I'm going to talk about why Josephson junction on indium arsenide quantum well, missing Shapiro step in non-topological regime, which is a slightly surprising situation since missing Shapiro step are typically associated with 4-pi periodicity of the current phase relationship, which has been predicted to occur in topologically non-trivial material. So in those material, one expects to see a 4-pi periodic component in the current phase relationship and a 2-pi periodic component. This arises from the fact that the topological gapless and direct bound state actually have a protected crossing at zero energy at a phase difference of pi and are usually disconnected from the continuum at 0 and 2 pi. As a consequence, if you start from 0 phase bias and you ramp up the phase bias, you go across the crossing and end up in the high energy state at 2 pi, which means that in order to observe that 4 pi periodicity, you need to go faster than the relaxation from this state to the lower state. As a consequence, DC measurements are not applicable, and one needs to rely to microwave techniques such as noise emission or Shapiro step experiment, as I'm going to discuss today. So Shapiro step experiment are the good way to probe the periodicity of the minima of the current phase relationship. A good way to understand that is to consider the relatively shunted junction model, in which we split the current flowing through a junction between a part carried by the superconducting state and a normal part characterized by the normal resistance of the junction. When one plugs in the relationship between the voltage and the phase difference, one arrives to simply the equation of a motion for a particle in a tilted washboard potential. If we have both 2 pi and 4 pi periodicity in the current phase relationship, since that's the current phase that is going to dictate the profile of the washboard, we're going to have shallow minimum and deep minimum. And so what will happen when we drive the system using microwave is that we're going to vary the tilt of our tilted washboard potential. At low frequency, the particle is going to go from one deep minimum to the next deep minimum, hence advancing by a multiple of 4 pi per period of the microwave. At higher frequency, we're going to get trapped in every single minimum, and so we're going to advance only by 2 pi during each period. If we advance by 2 pi for each period, you are going to see a voltage step of hf over 2e. If you advance by 4 pi, it's going to be hf over e, which is why Shapiro step is a good way to probe the periodicity of the CPR. So such experiments have been carried out, typically on topological insulator materials such as mercury telluride, both in the 3D topological insulator regime and the 2D topological insulator regime, and people have observed indeed missing Shapiro steps. So we see here that the odd Shapiro steps that would correspond to advance by a multiple of 2 pi are actually suppressed. Our system is quite a bit different. We are studying indium arsenide surface quantum well, and I'm going to discuss today 2 different layers. In one, we have a capping layer of 2 nanometers. In the other, we have a capping layer of 10 nanometers of indium gallium arsenide. The first was indium aluminum arsenide. This is just to show you that what we observe is not 4-point resistance measurement in dilution fridges, and our sample is current bias. We apply the microwave either directly on the bias line or using an X-by antenna. And once again, I would like to point out that those samples are completely topologically trivial. One can use such quantum well to study topological phase transition, but in order to reach that regime, one needs a strong in-plane magnetic field, and here we work at 0 in-plane magnetic field. So first, what can we learn from the DC measurement? So here you just have a VI characteristic per junction, so from which we can extract the critical current, which is of the order of several microamperes, the normal resistance extracted from the high bias fit, linear fit, and the intercept that give us the excess current, which is directly related to the transparency of the superconductor-semiconductor interface. So first, you can notice that the junction is hysteretic. The forward and backward trace do not overlap. We'll come back to that later. That's a fairly important point. In addition to that, since we can extract all parameters, we can notice that the product of the critical current by the normal resistance is larger than twice the aluminum superconducting gap. meaning that we truly have high quality junction with high transparency. This is also encoded in the excess current for just the semiconducting to superconducting interface by the product of the excess current by the normal resistance, which is in excess of the aluminum superconducting gap. Finally, the current density is relatively homogeneous, as can be seen from the Fraunhofer pattern that match the expectation drawn in orange. So now let's move on to actual Shapiro step experiment. So we carried those on two different samples. So sample A with the aluminum arsenide capping layer, and sample B with the indium gallium arsenide capping layer. So at low frequency in the VI, you can notice that at low power, the first step appeared to be missing both of the cold and odd branch. Here we are ramping from negative bias to positive bias. We can see the same thing on sample B. Here the first step appeared to be suppressed. And we can also study the dependence on the microwave power of that feature by plotting an histogram of the voltage as a function of the microwave power. And here we see that the first step is absent in both samples. And actually on sample B, you can see that the third step is also partially suppressed, which is another interesting signature. However, as I explained before, when we go to higher frequency, we recover all steps, as can be seen both in the line cut and the histograms. However, as I said, our junctions are hysteretic, and we have to be careful about that, because hysteresis can very easily lead to a missing first Shapiro step. It cannot really affect the third step, so there's still something interesting going on with sample B, but for sample A, we have to be careful. First, when we are on the cold electron branch, meaning that we are going from zero to finite bias, so we start in the superconducting state. Because the hysteresis in our junction is thermal in nature, as we will see right after, what can happen is that we're going to go to a large current, then we're going to switch out of the superconducting state and heat up the junction quite a lot, leading to an actual reduced superconducting critical current, but we cannot see. However, this means that the voltage jump we have is relatively large and can hide one step or even several steps. On the odd electron branch, we can have something similar. It's slightly more subtle in the sense that now it's an early retrapping. We start from a finite temperature system that we slowly cool down, and at one point it can enter back into the superconducting state, but this can happen before the voltage across the junction reaches zero. So once again, we can have a voltage jump, and we need to be careful that we're not missing a step because of this. In order to clean that possible issue, we have performed experiment at elevated temperature. So here we plot the critical current product by the normal resistance as a function of temperature on both the cold and odd branch. We see that the cold branch product is decreasing, but the odd branch product is mostly insensitive to temperature, since the sample effective temperature is much higher than the temperature of the fridge. When we reach 650 millikelvin, the system is completely hysteresis-free, as can be seen on those forward and backward traces. Now we can reproduce our Shapiro step experiment in an hysteresis-free setup. So here you see that the second step developed very clearly, the third step also, but the first step is fully suppressed, both on the cold and odd branch, which are anyway now equivalent. And if we plot the histogram of the voltage, we see very clearly that the first step is fully suppressed across the full power range. If we go now to higher frequency, we see once again that we have all steps. And this experiment has been carried out on another device on the same chip as sample A1 and the main sample A2. So now the question is, why can we see that those missing Shapiro steps that hint at a 4 pi periodic behavior? So we're not in a topological state, so we don't have a protected crossing at a phase of pi and zero energy. However, what can happen is that if the junction is highly transparent, the gap between the lower and upper Andreev bond state can be small. Typically, you need high transparency of the order of 98 or even higher. And if you have such a small gap, since we're doing a dynamic experiment, we can go through it through a Landau-Zinner transition. Will probability depend on the gap, the transparency, and the instantaneous voltage at the time of crossing. People have often used the average voltage, which is directly related to the frequency, but that is a very large underestimate of the actual instantaneous voltage. Doing RSD simulation or theoretical eggs have shown that basically that voltage we care about, that instantaneous voltage marked by the black arrow, is roughly independent on frequency and is of the order of twice the gap. So in that case, about 100 gigahertz, much higher than what we would expect. This means that, yes, we do have a constraint on transparency, but it's the order of 98%, not 99.99% as was considered before. However, remains one question: why don't we relax through the continuum? It turns out it's related to the geometry of our junction. For mode with a lot, typically we can have trajectory going through the wall junction, which means that for those modes, the junction is going to appear as a long junction. And as can be seen from type adding simulation, those modes are going to be fairly well decoupled from the continuum, but still present a crossing at a phase of pi. So as a conclusion, we believe this is the first observation of missing Shapiro step in an adaptively trivial Josephson junction, where it's not due to system hysteresis and can be attributed to Landau-Zinner transition for long junction modes. Finally, I would say that the frequency dependence suggests only a small number of modes need to contribute for this to be observable. This suggests caution when attributing missing steps to non-trivial topology. This work has been published in Nature Communication. If you want to know more, you can also assist Professor Javachabay's talk in X58. Thank you for your attention.
Thank you, Matthew. So for the audience, if you have questions, please type them in the widgets right next to the live screen so that we'll be able to see it. Okay, thank you, Matthew.
Thanks.
So our next